O exemplo do Brasil e China está no listado que dá para chegar para o resto do BRICS e dizer assim, você quer sucesso, abraça e...
Sim. A China é um caso excepcional de sucesso. E o Brasil só corrobora isso, fala, ó, também estou surfando dessa onda e acho que vale a pena. Porque nesse evento que eu falei de São Paulo Growth, eles assinaram um fundo de colaboração entre Brasil e China mais profundo. Assim. Mas o resultado, bastante de
Hello, Sama, can you hear us?
Aí todo mundo está querendo resolver um problema. Só que cada um já tem um background de como ele acha que aquele problema deve ser resolvido da melhor forma possível. Aí cada um propõe uma coisa, o outro debate. Então, é muito moroso o desenvolvimento, muito lento. Mas também quando se converte para uma solução final, é o estado da arte.
Muito forte a solução.
É muito forte. Então, assim, porque assim, o mais valioso não é você, eu entendo que o mais valioso para quem quer acompanhar não é você olhar a solução final, mas você vê o processo de desenvolvimento.
Não.
Você aprende várias coisas que talvez você não aprenderia em nenhum lugar. Você consegue ver como o cara vê, como eles trabalham no vídeo, da forma como ele apresenta, como que é a forma de entender, ou de negociar, ou de expor um conteúdo técnico, ou de justificar que como que eles rodam os certos, qual é o Microsoft. Você conecta para ver como que é a operação ou o trabalho feito em cada uma dessas empresas. Então, se você observar desse ponto de vista,
You are muted, just in case.
É um recurso que você não acha em nenhum lugar do mundo. Nenhum lugar do mundo. Eu falo para os alunos, quando eu falo para o aluno, cara, não pensa duas vezes. Entra na reunião, senta e olha. Não precisa fazer mais nada. Eu falo, não, estou fazendo isso. Sabe? Você vai aprender. Você vai aprender. Lê da reunião, lê a lista de e-mail. Não consegue acompanhar a lista de e-mail? O que eu faço? Eu tenho que acompanhar toda a lista de e-mail.
Hi, Osama, can you hear me now?
Eu deixei o chat GPT acessar a minha lista de e-mail.
Hello?
Bom dia, sabe? Vamos lá. Aí eu peço um agente lá no chat GPT.
Tudo bom, Gessel? Como é? Sou Leonardo. Tudo bem?
Eu trouxe no pendrive a
Tá ótimo.
que vai ser segunda, né?
Isso, a gente coloca ali.
Amanhã, 8 horas da manhã, chega lá.
Só precisamos descobrir por que o microfone não está funcionando.
Organizado pelo lista de e-mail. Fala o que aconteceu aqui.
Hello, Osama, can you hear me now?
Yes, I hear you very well.
Okay,
So,
can you hear
is my
me
voice clear?
still? Can you still hear me?
Yeah, yeah.
Okay, great. I know what was wrong here. We can see you. We can hear you.
Okay.
So
Perfect.
everything is fine. Unfortunately, I cannot show the public here to you right now because the camera is being used by OBS Studio to stream everything to YouTube, right? But I'll make sure that I join the Google Meet session on my notebook as well, so at least you can have some facial feedback from myself. Not the best picture that you would be looking today, but it's at least some feedback.
Sure.
Yeah, let's just wait. I think we have a few more minutes, right? I will just arrange things here.
Okay, sounds good. Let me know when we start, so I'm ready for that.
Good, thank you.
Thanks.
So, Sama, are you able to share your presentation on your screen?
Sure, sure. Yeah. So,
Great, yeah.
do you see the slides?
Yes, we can.
Okay. Awesome.
So hopefully you can see me now.
Yes.
Okay, good.
Great.
All right, I think we are good. We can start. Usama, so Usama is speaking, will present to us from Germany. He is a researcher and professor at the University of Dresden. So Usama, please go ahead.
Yeah, right. Thank you very much. And I'm sorry I couldn't be there in Brazil. I would love to be there, hopefully in some next version of this. So this work is about attested TLS protocols for confidential computing. And we have been working on this, exploring its design space, trade-offs between different designs, and the formal analysis. And this is joint work with number of folks which are written on this slide. So it's ongoing research as well as development work. So I have for today the following agenda. Namely, I will present the problem, what we are trying to solve, what is the motivation behind that, and then explain some parts of the approach that we have been doing, and the vulnerabilities that we found, the solutions for those, or the proposed solutions for those, and finally, a hot topic, which is about discussion. I presented this at the CCC Tech, and many people were annoyed. I hope I won't annoy some people here, but truth is truth after all, so we have to face it. Anyway, so confidential computing. There are a number of claims made around confidential computing, and one of those is that it protects the workload, namely this confidential workload, from other workloads, namely this sibling workload, and the hosting infrastructure, which is this, that is provided by the host, let's say on a public cloud, which is the hypervisor and the kernel and other things. So they are assumed to be untrusted, at least that's the way how it is marketed. And the use cases for that are, for instance, like single party, where you want to provision some data, some secrets to the confidential workload, and then do some processing on the cloud. And multi-party, for example, you have multiple data providers and multiple consumers who are getting the data, and you do some confidential processing within this confidential area of the cloud. So that's the high-level idea. And this doesn't work without architecturally defined attestation, which can be local or remote, particularly in the case of cloud scenario that I just described, that this is the public cloud. And within that, that is now your confidential workload. And you, as the verifying underlying party, this terminology is coming from RFC 9334, which means that the verifier and underlying party roles I have combined together to make it a simplistic view for this presentation. And the idea here is that now these are two different platforms. You, let's say, on your laptop device are trying to connect to something on the cloud, which is this part. And then there is a network in between you and the cloud. And in this case, what is applicable is this remote attestation rather than local attestation. And specifically, it's a technique for verifying underlying party, namely you, let's say, to evaluate the trustworthiness of the tester, which is the workload shown on the last slide. You want to ensure that it's really your workload and not someone else's workload. And remote attestation takes care of the boot time integrity typically, but also it can be used sometimes for runtime integrity. I will come back to this topic. So what happens here is that you, let's say, sending from your laptop, you send an attestation challenge to the tester. A tester gets back an evidence, and then you verify that evidence and send over your secrets or your sensitive data. So going through the network, it would be apparent to you that this has to go through some secure channel, and that secure channel is basically the TLS, Transport Layer Security Protocol. And how remote attestation distinguishes from TLS is what I described in this slide. Namely, for remote attestation, you have the hardware manufacturer as the trust anchor, and in the TLS protocol, there is a PKI infrastructure which has the certification authority as the trust anchor. So the processes are roughly look like this triangle where you have two entities trying to interact with each other. And in this case, for TLS protocol, these two roles are called server and client. And from this, you may see already why I have reduced the 3 roles of the RATs or remote attestation into 2. Namely, this fits together very nicely with TLS, and I can have some nice formal analysis of this to understand what is going on and how the entities are interacting with each other. Then we have, in this case, for remote attestation, there is a evidence which corresponds roughly directly to the certificate which is issued by the certification authority. And you see analogously that there is a signature with some key, which is the attestation key, over some data, which is namely the M for measurements, and the public key, which is within the attester, corresponding to the private key within the attester. And in this case, in TLS, as you might know, it's the identity, for instance, the FQDN, the fully qualified domain name, and the public key signed by the private key of the certification authority. The difference, if you see at a very high level, is that the certification authority keeps its private key. However, in case of remote attestation, the private key is given over to each and every device, which is where it becomes much more vulnerable as compared to certification authorities. So with this, basically the idea is that the 2 things are providing 2 different kinds of guarantees. Namely, one is providing you guarantee about identity, the PKI infrastructure. Another one is providing you guarantees about the state of that entity, and the 2 can be composed together. That's basically what is called as attested TLS. And there are 3 main categories in which this combination can be done, namely pre-handshake, intra-handshake, and post-handshake. In pre, the signatures of the claims that I showed on the last slide basically happens on before the TLS protocol has started. So this part is the TLS handshake protocol, client hello up to client finished. And in intra, it happens in between, and in post, it happens after the TLS protocol has finished. So why are these 3 categories so critical or so important? The reason is that they have very different security properties, very different even deployment models, and we can view it at a high level in 3 different layers, namely whether they change the protocol or not. And you see already that like intra changes the TLS protocol invasively, whereas the other 2 do not change it too much. And in deployment, for instance, pre-handshake requires a new entity, namely the certification authority or a trusted authority. And in application layer, changes in application layer are required, typically required for post-handshake attestation. So that's why this categorization, other than security, is also relevant from implementation perspective, that is the deployment and changes where they happen. So there is a lot of fragmentation in the industry, and this picture shows like different design options within pre, intra, and post, which is the top level view, how we view it. All the attested TLS protocols, you see a number of categorizations, and then final leaf nodes are the implementations. And this is only a subset of all of those. I have not exhaustively listed, if we exhaustively list them, that will probably blow up this slide. But the idea is that these are the main options, and the idea was to show that there is a fragmentation in industry and we need a standardized protocol. And how do we actually then evaluate all of these protocols to see which one to standardize? And the idea here is that we came up with these levels of assurance, namely, how do we, like everyone claims that, for instance, Intel will claim that our protocol is the best, this is the one that should be used. Others will claim similarly. And the idea is that how do we technically evaluate the security of each of those protocols? And this is the criteria that we have. Number 1, the open source implementation, informal specifications available or not, formal specifications available or not, and on these formal specifications, whether formal analysis has been done or not, and finally, whether formal verification has been done for the implementation or not. And this basically matches a lot with the EAL levels that are there, that what level of assurance you achieve with those. And this table shows that basically for pre, there is open source implementation, but no informal specifications available. We did its formalization together with Hannes, Arto, and Thomas, we did this work for formal analysis. And on the right side, basically in this column, you see that the open source implementation is available for TLS Attest, which is a standard candidate for standardization, which was proposed. And finally, Scone is one of the solutions which is unfortunately closed source, and it has no guarantees provided at this point in time. And I want to emphasize that open source is really a must for confidential computing, because when you want to attest, you need to have some reference values. And if you don't know what these reference values are, or if you cannot compute them on your own or a trusted device, it doesn't really make sense to have these, to trust these reference values. So you basically trust, rather than trusting this cloud, you are trusting somebody else. So it's just a shift of the trust, not really solving the problem of trust. Right, so with this, I want to, you might already know that from this table that there is motivation for formal analysis. Other than that, there is also standardization requirement at the TLS working group where this work is most relevant. Namely, the formal analysis trials team, they have a panel of formal method experts who see at the protocol extension whether it requires formal analysis or not. And this protocol's attested TLS protocol basically makes the changes as deep as the TLS key hierarchy, so definitely it needs formal analysis. And formal analysis also brings more clarity in the legal requirements, for example, GDPR. So if we are using this for confidential computing, how does it satisfy the GDPR requirements when data is going from EU to the outside and so on, these kind of handshakes. And it has applications in confidential AI training and inference. So there it's also important that the confidential data is protected, and formal analysis can provide good guarantees on that. So with this, I will switch over to the approach part. In the first part, I have explained that why this problem is important, where we started and so on, how we got into the formal analysis, and now I will explain a bit about what approach we took, because most of the people in the team that I listed on the first slide are not formal method experts, so they are protocol designers mostly. And the typical pain points of the protocol designers who are typically with engineering background is that it's really hard to learn all these formal method tools to do the analysis themselves. And for a formal methods expert, let's say I call that a verifier, the typical pain points are that even if he has mathematical background and expertise of formal methods, it requires for him to understand the whole system, right? Like it's not just a simple attested TLS protocol that I'm combining TLS with remote attestation. It's a whole bunch of complexity underneath that system that needs to be taken care of. Otherwise, one can end up with a nice mathematical theorem which has no practical value. So it's really a challenge that one has to understand all the system, whole system dynamics rather than just a protocol. So the key idea that we have is protocol designer in the loop-based formal analysis, which means that we have in the formal analysis taken these protocol designers in the loop. That is, we move back and forth, we keep discussing all the results that we get at an abstracted level that the designers can also understand. And this brings benefits for both, namely for the protocol designers, they get better explanations and deeper insight rather than just a bunch of theorems which would most likely, these bunch of theorems would make no sense to them. To what do I really get out of that? And also the benefits for verifier, like he doesn't necessarily have to go to the whole system dynamics in order to just verify one thing. Getting it in the loop makes the formal model more realistic, closer to reality, and therefore much more useful in the real world. So the approach that we followed was that we did pictorial representation of the valid and invalid traces. So that's something coming from mathematical background, which is describing in a protocol form converting these traces into protocols such that they can see, rather than these theorems, they can see that how the attacker, for instance, is taking control of the protocol or using the protocol to invalidate the security. And the approach makes it simpler, I would say, at least, because it's just logical familiarity that one has to have. I'm talking about the protocol designers who are, just as a reminder, only engineering background. And with these pictures and this logic background, one can try to get at least much more insights rather than just theorems. So I will not go into the details of all of that, but it was just to show you roughly how we approached or tackled this problem together in collaboration. And I will now describe a bit more abstractly of all of these things. So the main keys which are involved in this protocol are attestation key, of course, coming from the remote attestation side. And then there are a couple of keys which are involved from the TLS side, TLS identity key, namely the typical long-term key for TLS, which is CS certified, the PK infrastructure, no change here. And then an ephemeral key, which identifies, for example, the workload that I showed on the first slide. So this is going to identify that specific workload instance rather than whole. So this is identifying that device, or let's say that specific machine. And this is identifying a specific PM instance on top of that machine. And the distinction here is that since this is CS certified and this is self-issued. Right, so the threat model here is that any of those three keys can be leaked. For instance, attestation key is the most protected one, but research has shown, for example, foreshadow that this can also be leaked. We have the standard TLS model, threat model here, which is that the weak Diffie-Hellman, weak hashes, and so on, hash collisions, and others. And the assumptions are complementary to the protocol design, meaning that we have made a few assumptions which have to come from the system itself. Namely, there are no weaknesses in the generation of claims. If there are any weaknesses, of course, then the protocol cannot do anything. So that's kind of complementary to the protocol design. And the verifying line party, recall my first picture, so that's you who is sending data to the cloud. For instance, you are, let's say, provisioned with the reference values. You know exact reference values. Let's say you have that open source code, and then you can compute the reference values on your own machine, which you trust. And you have the public part of the attestation key corresponding to this key with which the attester will sign, and also the public certification authority key. And one important assumption is that the time of check to time of use attacks are out of scope. So that also needs some guarantees from the system underneath, so which cannot individually be solved at the protocol design. The time between sending and receiving, so this is really the bottleneck from protocol perspective. So with this threat model, we, at a very high level, lay out what informal security goals we want. Of course, we want to maintain all the TLS properties. The FAT analysis that I mentioned for TLS working group also requires this. Sorry, that there is no, that any extension of TLS should preserve all these properties. And in particular, server authentication, that I know which server I'm talking to. From remote attestation, we formulated the following goals, namely integrity of evidence, that the evidence does not change during the transition, conveyance from the attester to the verifying line party, freshness of evidence, that the evidence is bound to a specific remote attestation interaction, and finally the refresh of evidence, meaning that I can repeatedly track the runtime changes. So the changes that are happening at the runtime, for instance, at the workload level and at the platform level, are both taken care of, and I can repeatedly do that at any point in time whenever I want. Then there are some composition goals that we combine the two things, remote attestation and TLS. And there the important thing is that the remote attestation should be bound to the TLS protocol, which means that more specifically, which means that binding of the evidence to that specific TLS session such that it's not usable in other sessions, which provides very strong guarantee that even if that evidence is, that specific session is broken, others cannot use it or misuse it. And finally, that the evidence is generated by the same server that is authenticated, which means that I authenticated using PKI, some server, and the evidence is also originating from that specific machine. So it avoids the relay attack. So this freshness of evidence was related to replay, and this one is related to relay, that the machine I talk to is the same machine that generated it and not some other machine. So that's a really important goal. Right, so with these properties, basically, we found two main vulnerabilities, which I will describe at high level. The first one is the replay attack, which is that in the first interaction, it used good state evidence. And in the second, before the second interaction, the TCP was changed or it was compromised, and it's no longer as you expected it to be. And then it could, if you don't have that freshness check, it can still replay the old good state and it's still stale. But if the verifying client party doesn't have any freshness check, it will accept this evidence. It will continue to believe that the attested is in good state, while in reality, it is not in a good state. The second one is related to the use of remote attestation only, which is related to the standard proposal, which was section 6.1 in that remote attestation only option. And the idea is that this is the client, this is you, for instance, talking to the cloud, and you want to access cloud.example.com. You get back an evidence, and just a second. Sorry for that, I'm going out of charging. Okay. The idea is that basically the evidence can then be, because the evidence just says that this has these measurements. It doesn't say anything about the identity of that specific entity. And because of this, it can be rerouted to any random dictatorship, for instance, random.example.com instead of cloud.example.com. And if the attestation key for that specific machine is broken, the client has no guarantees whatsoever on that. And this leads us to a conclusion that basically, instead of having one specific machine in your trusted computing base, you basically have all the machines in the world in your trusted computing base. If one machine out of all these machines in the world is broken, basically it breaks all the guarantees for you. And that's what I call as identity crisis, namely exactly what I mentioned, with the assumption that the corresponding certificate for that key has not yet been added to the revocation list. With that, I will show quickly a couple of solutions that we have in this space, namely one can augment rather than replace server authentication, which is basically meaning that use both chains and combine them together, PKI for identity and evidence for the integrity of the computing environment. They can both together provide stronger guarantees. And the problem here is that certificate verify message of TLS protocol is not extensible. You cannot provide proof of possession of the both keys which are on this slide. And for that, basically we proposed 5 solutions in intra-handshake and 1 solution in post-handshake. And mainly the idea was to do this in the TLS working group, and this one has now is the direction forward which we are seeing that can be done outside the TLS working group, where we have where we had in the last IETF a COF session where we defined this idea that we can have a working group specifically targeted to this solution, which uses RFC 9261. Use standard TLS handshake, and then on top of that, use authenticator request and authenticator to provide the evidence. So coming to the final point, which is about the discussion on can the CSP really be out of the TCP? And this is the part, as I said before, may annoy some of the people, but the point really is that we talk a lot about confidential computing based on the cloud service provider out of the TCP. But is it really realistic? Like in all public cloud cases, CSP is trusted for availability. Like you have to have guarantees from the CSP on that. There is no way around on that. Machine identifier, what that identity of machine is assigned by the CSP itself. So by saying that it's out of the TCP, we basically violate the host affinity requirements of data sovereignty regulations. Also, we trust the CSP for location because it's the only source of truth that can give us location. No other entity can provide us that guarantee. And by having CSP out of TCP, we basically violate the location affinity requirement of data residency regulations. More technically, CSP is trusted for any part of the boot software that is not open source and not independently reproducible, meaning that I could have some piece of code that's not available to the customers, and then I can put backdoors in there. And also, specifically, I will show on the next slide the virtual TPM. Without knowing the configurations, I cannot be sure what exactly it is doing and what exactly it is measuring even, like the runtime measurements for remote attestation. If the VTPM, which is actually doing the measurements, and the VTPM itself is in control of the cloud provider, how can the cloud provider be out of the TCP? For instance, for AWS, for Google, both of them have the VTPM outside the DE. And thirdly, generation of evidence, like I had a recent thought on this, that basically the R data field is the one where you get that E. And Microsoft doesn't allow you to fetch that evidence directly, which means that they put in that R data field and they put in some extra fields, which I will show you in the next slides. But the idea here is that what stops Microsoft from putting in their own key for the VM, and then you connect to that specific VM which Microsoft has given you and not the one that you desire. So this field is really critical, and it's really CSP is the root of trust for this. So as I will show you. Also, two related points are that the VTPM, which in the case of Microsoft Azure, is doing all the measurements for the application and the OS measured by VTPM. The point is, for the trusted relationships, who owns the seed for this endorsement key for the VTPM? And who signs the endorsement key for VTPM? Both of them remain in the TCP. And it's Microsoft, as we will see in this slide. For instance, this is the Intel as root of trust. This is the Intel's certificate chain. And on the right, this is Microsoft as root of trust for OpenHCL, which is their offering. And the whole trust basically starts with Microsoft, which have the for the VTPM, they issue a VTPM AK certificate, and then they issue a VTPM code. And this is the thing that I was mentioning, that basically they put in two keys, which are the public part of the attestation key for VTPM. This V is for VTPM. And the public part of the endorsement key of the VTPM into this part for the KD code, which is the R data. And this key was the one with which I established the trust. What stops Microsoft from exactly changing this specific key is the real question. So so they remain, of course, in the TCP. And other than that, so there are no publicly available specifications for the provisioning phase, and the security release phase uses Microsoft Azure Attestation and Azure Key Vault. Both of them require trust in Microsoft. And to finally summarize it, so we saw that the formal license is required for standardization. Protocol designer in the loop-based formal analysis, I gave you some intuition of how we collaborate. And I showed you replay and diversion attacks for both of the protocols that we analyzed. And then I explained post-handshake attestation is a more suitable candidate for use cases requiring runtime posture assessment. You build a TLS channel, and then on top of that, you can do runtime posture assessment for PTT as many times as you want. And finally, I explained that the threat model claimed by CCC is trivially broken with the help of the examples from Microsoft and also other cloud providers, as I showed you. The current status is that we had a successful BOF in the last IETF, and in the next IETF, we are hoping that we will have a working group, and in that we will basically, the charter itself includes formal analysis. And the vision I have is that from ProVerif, which is the tool that we are currently using, we can use a cryptographic tool, which is CryptoVerif, which uses similar semantics and then moves to the cryptographic proof. And from there, we can generate a formally verified code implementation in F* that one can use for implementation. And that would be a nice path because we will have everything formally verified. If some of the requirements change, if the code is required to change, that you can do all of that automatically, generating and ending up in a formally verified code. So there are some pointers to some resources and some references, and I really want to acknowledge all the co-authors and contributors who have put in their hearts into this, and thanks a lot. I am open to any questions or discussions that you would like to have.
Okay, thank you. Questions to someone?
Sorry, your voice is not very clear.
Yeah, it's just because I'm in the back. Hopefully it's better now.
Yeah, it's better now. Yeah.
So I do have a question actually.
Sure.
You mentioned that, of course, open source is very important to make all these secure and transparent, and to make sure that anyone can really verify the environment they are running. But you mentioned some points in a previous slide, like the availability or even the location of the servers. So these are things that will not be solved by open source. Exactly this one, right?
Mm-hmm. Yeah.
So
yeah.
Do you have a suggestion, or what is the solution then?
So our understanding currently is that from all of this, what I wanted to kind of say is that basically CSP is trusted.
Right.
So the whole threat model which says that CSP is out of the TCP doesn't make any sense. So you cannot eliminate, even if you by technical means achieve those, you cannot really, or I don't see any way how one can eliminate the CSP from these things. So it's only the CSP who is assigning an identifier. It's giving you location, it's giving you availability. And my kind of conclusion here is that the threat model itself needs to be changed. You can definitely protect from the sibling workloads, that's fine. But this part is a bit of a marketing claim that we can protect from there. I don't see how it will be achieved in real life. That's kind of my current understanding.
Okay, but at least, if you have open source and you can generate your reference values, you can at least make sure that you are running on the correct thing, right? On the expected hardware and software stack.
Right. So instead of that, I have a better kind of a proposal, which is namely even better than open source, is that have some specifications available.
Yeah.
Do formalize these specifications and do some formal analysis on that. Yeah. That would give us much more assurance than just having open source.
Yeah, of course.
So this is the level I visualize that should be like we have achieved up to here, but not yet at the level of implementation, which was the last slide showing the vision. And once we achieve there, I think that would be a better route than having to say that, okay, CSP is out of the TCP, so have each of those complete blocks formally verified, and then we have much more guarantees rather than just saying that, okay, trust us that we are out of the TCP. So that's how I visualize this thing.
Okay, thank you. Any other questions? No. Thank you, Osama.
Okay, thanks so much.
So next session will be in conjunction with the seminar series, starting in 10 minutes. Vamos pro Você pode copiar aqui? Isso. E é sempre a segunda, né? Que dá certo. Bom, acho que esse é o seu pendrive.
Isso. Tá na raiz, chama GC 25 FOSForums.
Talvez agora, são datas em português, né?
Isso. 9 megabytes. Vocês estão colocando site?
Sim.
Olha, que eu vi que aqui não tem nenhum relógio.
Não, então não tem.
Vou colocar meu celular aqui em cima. De vez em quando eu deixo.
Porque eu posso fazer, te avisar, eu 10 minutos.
Você deixa eu ir.
Beleza. É. Passador. Não, você pode usar o passador se você quiser.
Aqui tá do celular que eu vi.
Tá. Tem mais um último vídeo. Porque cada segundo.